Thank you very much for the invitation. So what I'm talking about is joint work with Vivek Scheme from Berkeley for the first and more substantial part, and then for the second part, which is still work in progress. Also, I mean, besides Vivek Shende, also Filippo Viviani from Roma 3. And so this is a talk on topology of algebraic varieties in the crudest sense, as it deals with the Betti numbers of algebraic varieties, complex algebraic varieties, actually. So to say that all varieties are over C, and the groups are with rational. So let me first start from something very elementary. So let's talk about what the so-called Mcdonald formula for a non-singular curve. So say that C, projective non-singular. Now we have several objects associated with the curve, and this is, so we have the Picard schemes of C, so we can consider them as parametrizing indifferently line bundles on C of degree D, or, which is the same, rank 1 torsion-free sheaves of degree D. And similarly, we have the symmetric products, which can be considered as parametrizing indifferently effective degree D cycles, 0 cycles, or, which is the same, subschemes, 0-dimensional subschemes of C of co-length, of length, whatever, D. And these things just coincide on a smooth curve because, I mean, for obvious reasons. And so these are all non-singular. This symmetric product because of basically Newton's theorem on symmetric functions. The non-singular and complete, actually, projective. And these are also, well, for D equals 0, this is a commutative algebraic group. And for D different from 0, this is a torsor over pic 0. So what about the cohomology groups? Well, this is quite easy. So the cohomology groups of any Picard thing is just direct sum of lambda I h1 minus I. So h1, I mean first cohomology group of C. I think C is connected, but doesn't really matter. And minus E means only that I put actually the Hodge structure in degree D. And Mcdonald's formula, I mean, a special case of Mcdonald's formula tells me that the cohomology groups of the symmetric products are a direct sum of something which I'll call SID of H1, still in degree D, where SID is this linear algebra operation. So I take the ith wedge, and then I sum ith wedge minus 2, and I tate shift it by minus 1, and then I go on, minus 4 V, and then I shift it by minus 2, and so on. So this is OK for I less than or equal to D, whereas S, say, A plus D, D, V is just S of D minus A, D of V shifted by, tate shifted by minus A. So in particular, well, we say that everything is governed by this H1 via linear algebra operation, and then there is this relation between cohomology groups of the Picard and cohomology groups of the symmetric product, and there is a compact form of this formula, which is the following. So we write a generating sequence, generating sequence. So QD H dot of CD, and this is just, so let's see. So what is the, yeah, maybe this is the sum for I from 0 to 2G, or G is the genus of the curve, QI wedge I H1 minus I, and then here you put something like this. So you develop this in the obvious way, and then you get an equality. Just remark, I mean, this term is not mysterious, because this, if you develop this, you get basically the sum of projective spaces Q to the D, which is consistent with the fact that the symmetric product of P1 is just PD. Okay, so I will refer to this as the Mcdonald formula. And well, and you see easily that for D bigger than 2G minus 2, then you see that the cohomology of the Hilbert scheme is like cohomology of the Picard times cohomology of a projective space, which is consistent with the fact that you have an Abel-Jacobi map, and this becomes a projective fibration for D big enough. So, so this is compatible, and of course it better be. And so we can do this in the relative setting. So if we have, say, so smooth families, smooth family of projective non-singular curves, and then you have R1, which is first direct image of the constant shift. This is a local system. And then in this case, Macdonald's formula just upgrades to a formula in variations of Hodge structures. So this of course underlies a variation of Hodge structures of weight 1. So you also have for any d a relative Picard fibration. And so I'll call pi j this thing here, and you have a relative symmetric product, which I refer to. I'll put square brackets because later they become square brackets. And then you know by the refined version of E2 degeneration, I mean that then you have isomorphisms in the right category. So for instance, this is isomorphic to lambda I R1 minus I, and similarly this is isomorphic to Si d R1 minus I. So this by the linear degenerescence, and then I think that's enough. Okay. Actually, in this case, the splitting can be even made canonical, because for family of abelian varieties and close relatives, this works. So then you can just rewrite this, upgrade this Mcdonald formula just at the level of an equality of variations of Hodge structures. So just put Rp d lower star of Q, and here you put R1, and here you interpret this as the constant shift over what is B, and here you interpret this as the constant shift twisted by -1 and in degree d. So this is an equality of variations of Hodge structures, pure variations of Hodge structures. Okay, so far so good. What happens if C is now singular? So if C is now singular, and I'll say more hypotheses coming soon. So in this case, you still can consider line bundles of degree D, and these are maybe parameterized by something. But then you have also rank 1 torsion free sheaves, and which may very well not be line bundles. Let me give an example. So for example, let's take C, just a nodal curve, and C tilde the normalization. And so for instance, if you take the node and you consider the ideal sheaf of the node, this is certainly rank 1 and torsion free, but certainly not invertible. And similarly, if you consider the symmetric product, say, of length 2, and then you can consider the cycle 2 times the singular point, There are many subschemes. Actually, I'll tell you how many. Supported, I mean, with associated cycles. Twice the nodes, and basically every subscheme by xy y square, every subscheme of this kind is contained, even though it doesn't look. If you try to draw a picture, you think of this as a tangent vector, so you think it's not contained, but it's actually contained. It's only the picture which is not right. So actually, there's a whole P1. So there's a P1 of length 2, n times the node. There's a chain of n minus 1 copies of P1. And there are n plus 1 preferred points, which corresponds to monomial ideals. So let me be a bit vague at this point. So I'll say that Picard-D parameterizes these objects, whereas these objects are parameterized by a different thing, which is usually denoted JC bar, maybe D, but I will soon skip this, which is called the compactified Jacobian. So in order for this to be a bona fide variety, you have to make choices. So planar singularity is certainly very useful. So for the time being, let's also assume that C is irreducible. So if C is irreducible, so C is reduced and irreducible, it's an integral curve. So if C is irreducible, this is really a well-defined variety, which it has the same representability properties of the Jacobian of a curve, okay, and has dimension. So in this case, this exists. We know that it's irreducible. It is a locally complete intersection, and it also has an action of peak 0 of C, which is a group, an action with a dense orbit, open dense orbit, which is peak D of C. The action is just that you take a rank 1 torsion-free sheaf and you tensor with an invertible sheaf of degree 0. So we know this sort of things. So in this case, we have the symmetric. No, I didn't want to erase this. So we still have the symmetric product, which parameterizes effective degree D cycles. And now we have a new object, which is defined in good generality, which is the Hilbert scheme. And for the Hilbert scheme, also, there are theorems like this. So this is, I didn't say this. This is projective. Of course, if C is singular in general, peak 0 is an algebraic, singular and irreducible, is an algebraic group, but it's very often non-compact. Yeah. Okay, so this is a sort of a compactification of peak D. So what about this guy? We still have that it's projective. dimension D, irreducible, locally complete intersection, and has a dense open set which correspond to D distinct regular point of C.
For LCI, does that use the planar singularities?
Yeah. Everything about the Hilbert schemes boils down to one of the miracles in low-dimensional geometry, which is the fact that the Hilbert scheme of a surface is non-singular. So basically, you can sort of write down the precise number of equations cutting the Hilbert scheme of the curve inside the Hilbert scheme of the surface which locally contains C. Yeah. Okay, so we will concentrate on the compactified Jacobian and on the Hilbert schemes. So these varieties appear in several pretty interesting contexts. So from my point of view, the most interesting context in which the compactified Jacobian appears is as singular fibers of Hitching fibrations for the group, the general linear group, and in general, they tend to appear as singular fibers of algebraic completely integrable systems. And also, maybe I want just to remark that a close relative of this compactified Jacobian is an object which is very important in representation theory, which is the Fine-Springer fiber. Actually, if C has only one singular point, and and this singular point it's only branch, then the compactified Jacobian is homeomorphic to this Fine-Springer fiber. And actually, the motivation for what I'm going to tell you in a minute comes from the fact that the Hilbert schemes and the compactified Jacobians appear in two different ways to count curves in enumerative geometry. So I'm far from being an expert on this, so this was actually Shende's motivation. If you look at the pretty recent survey of Rahul Pandaripande and Richard Thomas, which is called 13 half ways for counting curves, you see that there are two ways which are called the Gopakumar-Vafa invariants and the Donaldson-Thomas invariants. So basically, Gopakumar-Vafa invariants counts curves involving Jacobian to count singular curves, whereas the Donaldson-Thomas counts curves in some setting with the Hilbert scheme. And there are conjectural relations between these two ways of counting curves, which in a way predict some relation between the Betti numbers of these two objects. And finally, I want to say that there is a very interesting circle of conjectures about the fact that if you take C, for instance, rational with a unique singular point, then you have the link of this singular point, which is, say, a knot if C is unibranched. So there are a lot of conjecture by Oblomkov, Rasmussen, Shende, and I think that's it, which relate the topology of the Hilbert scheme of the curve to invariants of the nodes, such as some variation of Humfly polynomials. So, there are very interesting things, and they're also very tricky to compute. So let me just give you an example of how tricky they are. So say that C is rational with a unique singular point say, yp minus xq with p and q coprime. So this ensures unibranch. So in this case, the compactified Jacobian has dimension. I didn't say what the dimension of the compactified Jacobian is, but, well, I say it implicitly because it contains the Picard as a dense thing. So it's the dimension of the compactified Jacobian is the arithmetic genus. So the dimension is, in this case, p minus 1, q minus 1 over 2. So in this case, it's known that the odd Betti numbers are 0. So therefore, the sum of the Betti numbers is just the Euler characteristic, which is like this. It's this number. So in this case, the compactified Jacobian has a paving by affine subspace. So you need to count these subspaces. But still, there's no closed formula for these Betti individual Betti numbers as a function of p and q. There is some work in progress that I know of by Oblankov and Yoon, but I haven't seen it. So just to give an example, which I will later use, if you have this singularity, then the numbers are like that. The Betti numbers are like that. So you have a B4, which is dimension 2. Okay, so what do I want to say? No, not that I know. I mean, you just have to count cells. I mean, you write basically this as a fixed point set in some Grossmanian for an action, and you have to count cells, but no. It has a paving by affine cells, yes. So, but to count the cell is far from trivial. So, so our question is the following. So still, C is irreducible. So is there a Mcdonald formula? Relating the Betti numbers of the compactified Jacobian. I will skip the D because, I mean, you go from one compactified Jacobian to another just by twisting by a line bundle of appropriate degree. So they're all isomorphic with the Betti numbers of the Hilbert scheme. So something like that. So, and the answer is yes, although in a subtle way. So a possible approach, I mean, the approach that that Shende and myself followed, this was also done independently by Davesh Maulik and Ziwei Yoon. So the approach is the following. So take a family. So include your singular curve in a family. So I ask that the family is big enough. And you can say how, I mean, what does it mean, big enough? So big enough means that I want that if I take the relative compactified Jacobian family and the relative Hilbert Scheme family, then I want the total space of these families, I want them to be non-singular. So this can be done. Okay. So this can be done. For example, if B is what we call locally versal. So locally versal, so let me say in words instead of writing down, is the following. So you have a deformation of C, which induces deformations of all the singular points. Okay? So you want that the deformations of all of these singular points are versal. Okay. So it has to be big enough. So if B is locally versal, then there are theorems, and for the compactified Jacobian, these are due to Fantecchi, Goethe, and Van Straten, and for the Hilbert scheme, these are due to Shende, which ensures that that the total spaces are actually non-singular. Actually, much more is really true. I mean, the deformation theory of this object is pretty well understood. So there are much more precise criteria to have these spaces non-singular, and probably I will come back to this later because they play a big role in the proof. Just to remark that, just as an example, having the total space of the family of curves non-singular is not enough. It's not enough, for instance, to say that this is non-singular. The example is simple. Just take a curve with two nodes and smooth it out in a one-dimensional family. So this certainly can be done. Okay. But if you then look at the family of length 2, then you are in big trouble, because if you take the scheme, which consists of node 1 plus node 2, you compute the Zariski tangent space. It's 2 here, so it's 4-dimensional. So you certainly can't have a 3-dimensional smooth family. Okay? So this is not smooth. I mean, this is singular. It's not locally versal, because it has to be versal for each of the singular points. So you have, yes, yeah, that's right, yes. So, so the condition is that, so if, let's see, so if T1 is the space of first order deformation, this maps to the direct sum of the local T1s of the singular points. Okay, so if you have a family, you have a map from the tangent space at B here, and you ask that this one is surjective, so on the direct sum. So to have a versal family, you need at least dimension 2. Yeah.
I mean, so here these questions are basically local. I mean, it doesn't matter.
No, yeah.
The rest of
Yeah, the rest. That's right. No. It's a local thing. Okay, so so we embed this guy in a family, and then we have some open set B0 inside B, where this is smooth. This is smooth family. So over the smooth family, we already know what happens. Okay? So we say that we have that r pi lower star j of q restricted to be 0 is a direct sum of these local systems, and r pi lower star d q restricted to be 0 is a direct sum of these local systems. And these are related by the Macdonald formula. Now, if you want to know what happens on all of B, then what you have is that this object will contain as a direct sum the intersection cohomology complexes of these local systems, and similarly this object will contain as a direct sum the intersection cohomology complexes of these local systems. So remark, I'm using the bad numbering convention. So this is the numbering convention according to which intersection complex of a local system restricted to the smooth part is L instead of L shifted back by the dimension. But well, luckily, at least in the irreducible case, this doesn't cause much trouble. Okay, so here I'm using the Bellinson-Bernstein, Bellin-Gabber decomposition theorem. And so this is a direct summand. So from our point of view, this means, for instance, that taking stock of cohomology sheaves at 0, for instance, here. So if I want, I consider HA of this guy by proper base change. This is HA of this guy here. So this will split into a sum. Well, this will contain, a sum of HA minus I of these intersection cohomology shifts of these local systems, and the same for the Hilbert scheme. And well, also notice, remember that this guy was something like lambda I R1 plus lambda I minus 2 R1 shifted by minus 1, and so on, and intersection cohomology is additive, so it splits into intersection cohomology of local systems which appear here. Okay? So here I'm taking the stock at 0. The same here. And actually, a bit more can be said in the sense that these vector spaces have a canonical mixed-Hodge structure, and this inclusion is an inclusion of mixed-Hodge structures. Okay, so the problem is that in general, this is a proper inclusion. So the general form of the decomposition theorem says that if you want to have equality, here you have to add some other intersection cohomologies of some local systems supported on some proper non-singular locally closed subset of B. And the same with this guy. Or with some shifts. With some shifts which would be hard to fix if using this wrong number. Okay. By the way, let me just notice that here you see that there is some further, even, I mean, regardless of this inclusion, you see that there is some further structure in these cohomology groups, because there is some sort of, well, it's a splitting, but actually more canonical, it's a filtration. Okay, so one cohomology class in HA can come from, I mean, you can keep track of which intersection cohomology of the local system is basically creating this class. So there is, I mean, this defines some, there's an obviously defined filtration on this thing here. Now the theorem, which is due to Shende and myself and independently to Maulik and Yoon, is that actually there's nothing here. So actually this is a special case of Go support theorem, which actually we reprove in this case, but this is the new part. So basically, I mean, even though in a very involved way, all the cohomology groups with rational coefficients of the Hilbert schemes and the compactified Jacobians are just determined on what happens on the singular locus. And what happens means a lot, because it means understanding the monodromy representation of this R1 and maybe the singularities of the complement of B0 in B. So this is the theorem. So it's a sort of support theorem for Hilbert schemes. So this means what I said, that the total space of a family of these families are non-singular, and C is irreducible. So this is a local theorem. I want to consider only close to the central point. And so in this case, we have equalities of this sort of things. And so in this sense, this generalizes the Mcdonald formula, because you can, so this guy is sum of HA minus I of this SI of R1. So in a way, stock at 0, the homology groups of the compactified Jacobian and of the Hilbert scheme just determine each. I mean, the ones of the compactified Jacobians determine that those of the Hilbert scheme. With this additional information that, I mean, you have to consider it, I mean, endowed with this filtration. So if you want to write a generating series, this will have two indices, actually, because you have to keep track of which system creates a cohomology class. So let me give you, go back to the example of x3, y3 minus x4. So you remember that we have these Betty numbers. So this guy comes from intersection cohomology over 0, which is actually a constant sheaf. This guy comes from intersection cohomology over 2. This guy comes from intersection cohomology over 6. This guy, okay, so there is one part which comes say, from the right thing. I mean, when I say this, I mean that H0 of these and so on. And then there is one other class which comes from the fact that H1 of this is different from 0. So in this case, what is called the perverse filtration is non-trivial in this degree. Okay. And actually, the circle of conjectures that I was telling you before relating the Hilbert scheme and these Humphrey polynomials of associated knots actually involve the perverse filtration. So to recover some part of the Humphrey polynomial, you don't only need the dimension of the Betti numbers, but also of the graded parts of the perverse filtration. So, let me remark first with an example, which may be fun for somebody, that in general, it is quite hard to understand what are the summands in the decomposition theorem. I mean, it's not something that you can really easily guess. So let me give an example. I'll draw it. So you take a two-dimensional disk, and then take a family of curves, which are here are elliptic curves, here are nodal curves, here are nodal curves, say, in the other direction, and here is a banana curve. Okay? No, I mean, so I was sort of joking. I meant that in general you have two vanishing cycles. So in this divisor you shrink one, and the other you shrink the other. Nothing serious. And so in this case, well, you write on the smooth locus, you have Q plus R1 minus 1 plus Q shifted by minus 2. And then you would guess that in order to account for the fact that this central curve has one more irreducible component, you might guess that that when you go to B, you have these things. And then maybe you should have something supported at 0 to account for this irreducible component. Okay? But in fact, you don't. In this case, the support theorem holds. And why this is that this extra component is accounted for by the magic of the intersection cohomology complex, which happens to have an H1 at 0. Which is different from 0. So this extra component is created just by the intersection cohomology. And notice that if you take a family, a general enough family passing through 0, then at this point, a support appears. Because when you restrict this IC, this splits into IC of R1, but it splits off another summand. So all this is related to the fact that the intersection cohomology doesn't commute with base change. The intersection cohomology of a restriction is not restriction of intersection cohomology. Okay, so, well, So what about the reducible case? I will just say a few words about the reducible case. So in the reducible case, so there are many problems. So first of all, the compactified Jacobian is a variety. I mean, in a bona fide variety. Only after choosing a stability condition. You cannot consider all rank 1 torsion-free sheaves on C, because you would get something really not of finite type, really not separated, really unpleasant. So you have to consider only rank 1 torsion-free sheaves which satisfy some further condition, and there's a whole set of work. I mean, there's a lot of work on the different stability conditions, so you have many compactified Jacobians, different compactified Jacobians. And so even, but after you choose a stability condition general enough, then you can, if you have a versal family of the curve, you can at least locally construct a family of relative compactified Jacobians. So then you notice easily that the support theorem, so support theorem, I mean something like that there are no summands supported on proper subvarieties. So this cannot hold for the Hilbert scheme. And the stupidest example is just a family of conics degenerate into a double line. So this is certainly versal, so it's OK. And the family C is, of course, the same thing as the Hilbert scheme of length 1. And here you have a support. You have a sheaf, skyscraper sheaf here to account for its extra component. I mean, this support must exist just out of pure thought, because, I mean, consider how you can construct a family. You start from a family MP1 and then blow up a point. But I cannot guess that I blew up a point just from what happened outside. So, I mean, something has to exist to distinguish between the trivial thing and so on. So yeah, well, I mean, whatever reasonable meaning to the compactified Jacobian you give, the compactified Jacobian of this will be a point.
Yeah, but I was saying, so there should be some support also for
No, no. If you look at the intersection, the compactified Jacobian family, this looks like this. If you, I mean, if you choose a polarization so that the compactified Jacobian.
But not in this case. I'm saying kind of the same type of argument is that you cannot say what's the compactified Jacobian.
Well, actually, you can. I mean, the cohomology group, you can't say what the compactified Jacobian as a variety is, but from the point of view just rational cohomology group, you actually can. Because, so in this case, the support theorem holds for the compactified Jacobian family, and this was also a bit, I mean, was noticed before by Chaudhua and Lumont. And but the support theorem certainly doesn't hold on the Hilbert scheme. But you sort of can save the thing, because it is actually possible, and this is what will be written in the paper with Shende and Viviani eventually. So it is actually possible to determine all the summands in the Hilbert Scheme family. And all these summands involve Hilbert schemes of lower degree of decompositions of your central curve into connected subcurves. So there's a very complicated formula which gives you all this summand. Okay? So actually, the interesting part of this is that there was a conjecture. Yeah, so let's start from say a nodal curve. So the family here looks like a normal crossing. So you have divisors corresponding to only one node. So only one node persisting and the others being smooth. But when you select a node, you can also normalize it. Okay, so on each set of this normal crossing divisor, you can have you correspondingly have a decomposition in curves. Then you look at those strata in which the decomposition is in connected curves, and those will support a summand. And magically enough, there was a conjectural formula coming from this Gopa-Kumar-Vafa versus Donaldson-Thomas invariants, and this actually predicts the right summands. So, I mean, doesn't prove it, but we think hopefully prove them, and that's fine. I'm 1 minute out of time. Let me go 2 minutes out of time. Sorry. Let me give the application which is dearest to my heart, which is the following. So you take surface, the total space of, so you start now from, let's call it, I will call it C, but it's a different one. This is a non-singular of genus bigger than 2, and then I take the total space of the canonical bundle, and then I look at the family, the so-called family of spectral curves here. So actually, this is basically the local system spectral curves of degree n. So this is the linear system n times C when you consider C as the zero section in this total line bundle. And then you have the compactified Jacobian family, which is now a very close relative of the Hitchin system. And you also have the Hilbert Scheme family. And the Hilbert Scheme family obviously map into a fixed variety, which is the Hilbert Scheme of the surface, because you just forget on which curve the subscheme is. And if you count, this is an affine fibration. Because basically a subscheme imposes independent conditions, so just cutting some linear space. So this means that these things have the same Betti numbers. So you can compute the cohomology groups up to a certain degree, the cohomology groups of these things. And thanks to the Mcdonald formula, you can compute the cohomology groups of these things and the dimension, I mean, okay? And this actually turned out to correspond to what is predicted by the so-called P equals W conjecture. So this tells you that, I mean, the number are right I mean, are consistent with the P equal W, I think, up to cohomological degree 2n, I think, which is very ridiculously small compared with the dimension of this thing, but still it's big enough, for instance, to contain all the generators of the cohomology. So this is an application which, I mean, is very dear to my heart because it's related to a sort of obsession of mine, which is this thing. Okay, so I think everybody's hungry, so I'll stop here. Thank you.